In this module, we will cover the aircraft's electrical system. We will start with a system overview. Next, we will cover the AC, DC, ground service, and standby systems. Following the system descriptions, we will look at the controls and indicators. Let's start with an overview of the electrical system. The electrical system consists of the AC system, the DC system, and standby system. AC electrical power can be supplied from one of four sources: either engine generator, the APU generator, or a ground power source. Transformer rectifiers, commonly known as TRs, convert AC power into DC power. The TRs are the primary source of DC power for the DC system. Two aircraft batteries provide an alternate source of DC power. Let's look at the AC system. The two engine-driven integrated drive generators, or IDGs, are the normal sources of power for the AC system. The number 1 IDG supplies transfer bus number 1, and the number 2 IDG supplies transfer bus number 2. The two transfer buses then distribute power to the airplane. The IDG contains the generator and drive system in a common housing. The IDG maintains a constant generator rotation speed at all engine speeds. The IDG has a self-contained oil system and generator drive disconnect mechanism. The IDG will automatically disconnect itself in the event of high oil temperature in the IDG. Each IDG supplies three-phase, 115-volt AC electrical power at a frequency of 400 Hz. The IDGs are rated at 90 kV when the aircraft is airborne, or 75 kV when the aircraft is on the ground. A generator control unit, or GCU, monitors the output of the IDG. The GCU will allow the generator to connect to the electrical system only if the generator output, both voltage and frequency, are within limits. There are no provisions for a paralleling electrical power source. Therefore, only one power source can be connected to a power bus at any given time. In this example, the IDGs are powering their respective transfer buses. Two other AC electrical sources can power the aircraft's electrical system: the APU and an external electrical ground power cart. The APU can also supply power to either transfer bus. The APU can power both AC transfer buses at the same time when the aircraft is on the ground or in flight. The APU can meet all of the electrical system demands when the aircraft is on the ground, and most of the demands while in flight. The APU supplies both transfer buses through bus tiebreakers, or BTBs. The APU generator is similar to the engine-driven generator, except that there is no IDG. The APU turbine speed is controlled to maintain a constant APU generator output. The APU also produces three-phase, 115-volt AC electrical power at a frequency of 400 Hz. An external electrical ground power unit, or GPU, can supply power to both transfer buses through the bus tiebreakers. The GPU is plugged in at an external AC power receptacle located on the lower right side of the fuselage near the nose gear wheel well. It is not possible to power one transfer bus from the APU and the other transfer bus from the ground power unit. The last selected power source will power both transfer buses. However, it is possible to power one transfer bus from the APU or GPU while the other transfer bus is powered by its respective IDG. In this example, the APU is powering both transfer buses through the bus tiebreakers. Click on the IDG2 to simulate an engine start and see the transfer of power for transfer bus 2 from the APU to IDG2. With the right engine operating, the bus tiebreaker trips off and the corresponding IDG begins powering transfer bus number 2. The bus tie system ensures that a transfer bus remains powered in the event the associated power source fails. If the source powering a transfer bus fails, the two bus tiebreakers will close and allow the transfer bus to be powered by the opposite transfer bus when the bus transfer switch is in the auto position. The transfer buses distribute power to various AC buses. Now let's look at the DC electrical system. The DC system is normally powered by a series of transformer rectifiers, or TRs, or the aircraft batteries. A TR converts 115 volt AC into 28 volt DC. There are three transformer rectifier units, TR1, TR2, and TR3. Transfer bus 1 powers TR1. Transfer bus 2 powers TR2 and TR3. However, if transfer bus 2 fails, TR3 will automatically receive power from transfer bus 1 through the TR3 transfer relay. Two TRs can supply the total DC load requirements. TR1 powers DC bus number 1 and the DC standby bus. TR2 powers DC bus number 2. TR3 is the primary source of power for the battery bus. It is also used as a backup power source for DC bus number 1, DC bus number 2, and the DC standby bus through the cross-bus tie relay. The DC circuit design is such that TRs 1 and 2 also provide backup power to each other through the cross-bus tie relay. A blocking diode prevents TR1 and TR2 from backing up TR3 to supply the battery bus. A DC cross-bus tie relay isolates TR1 from TR2 and 3. The purpose of this relay is to provide independent electrical power sources for the captain and first officer's navigation receivers and autoflight system. This is a requirement for Cat 2 and Cat 3A certification. The cross-bus tie relay opens when either condition exists. At glide slope capture during an autopilot or flight director ILS approach, or the bus transfer switch is placed in the off position. Two 24-volt NiCad batteries are located in the electronics compartment. They are used to supply DC power to start the APU and to power essential equipment when the aircraft has lost all electrical power. Two fully charged batteries can power the essential equipment for 60 minutes. The main and auxiliary batteries supply 30 minutes of power each. When the standby system is powered by the batteries, the main and auxiliary batteries are connected in parallel. At all other times, the auxiliary battery is isolated from the power distribution system. Two battery chargers maintain the battery's charge by converting 115 volts AC into 28 volts DC. They provide voltage that will maximize the battery charge. The main battery charger is normally powered by the ground service bus 2. The auxiliary battery charger is powered by ground service bus 1. When not charging the battery, the charger operates in a constant voltage TR mode. In this mode, the battery charger TR powers loads connected to the hot battery bus and the switched hot battery bus. If TR3 fails, the battery charger TR will also power the battery bus. With the loss of transfer bus 1 or the source of power to DC bus 1, the main and auxiliary battery chargers power the AC and DC standby buses. In the event of a loss of normal AC power, the battery will supply the following DC buses: battery bus, DC standby bus, hot battery bus, and switched hot battery bus. The standby system will be discussed later on in this module. The ground service buses supply electrical power to utility outlets, battery chargers, and cabin lighting. When the ground service bus is powered, the aircraft can be serviced without powering all the electrical systems. The ground service bus is powered by pressing the ground service switch located on the forward flight attendants panel. Let's look at the standby system. The AC standby bus is powered by transfer bus number 1. The DC standby bus is powered by the transformer rectifiers. The standby buses supply power to some of the essential systems in the event of a failure of normal electrical power. The backup power source for the standby AC and DC is the batteries. If normal power is lost from the AC transfer buses, the standby system will be powered by the batteries. The AC standby bus receives power from the batteries through the static inverter. The DC standby bus is powered directly from the batteries. Two fully charged batteries can provide a minimum of 60 minutes of standby power. Let's look at the controls and indicators for the electrical system. The control and indicator panels for the electrical system are located on the overhead panel. They include the generator drive and standby power control panel, the ground power panel, the bus switching panel, and the AC and DC meters control panel. Let's start with the generator drive and standby power control panel. The generator drive disconnect switch is used to disconnect the IDG. The red guard prevents an unintentional IDG disconnection. Positioning the switch to disconnect disconnects the IDG if electrical power is available and the associated engine start lever is in idle. Once disconnected with the switch, an IDG cannot be reconnected while in flight. A reset can only be accomplished on the ground by maintenance personnel. The IDG is monitored by the associated generator drive light. This light illuminates amber for one of the following conditions: IDG failure, engine shutdown, automatic disconnect due to high oil pressure, or IDG disconnected by the disconnect switch. The electrical annunciator and both master caution lights will also illuminate. The standby power switch controls the operation of the standby system and has three positions: battery, off, and auto. It is guarded in the auto position. The auto position arms the auto transfer feature of the system. This feature is available on the ground and in flight. The AC and DC standby buses will be powered from the batteries in the event of the loss of DC bus 1 or transfer bus 1. With the standby power switch off, the standby system is not powered. Whenever the AC standby bus is not powered, including when the standby power switch is in the off position, the standby power off light illuminates. The battery position forces both standby buses and the battery bus to be powered by the batteries regardless of any available power sources or whether the airplane is in flight or on the ground. We will now look at the bus switching panel. The generator switches are used to control the associated generator. The switch is spring-loaded to the center position. Momentarily positioning the generator switch to on connects the associated IDG to its respective transfer bus by closing the generator breaker. If the associated transfer bus is powered by another source, this source is removed. Click on the generator switch to see the effects of generator start. In this example, the APU is powering both transfer buses. When the generator switch was placed in the on position, the APU bus tie breaker opens and the engine generator circuit breaker closes, allowing the transfer bus to be powered by only one source. The associated generator off bus light is extinguished, indicating that the IDG is supplying the transfer bus. The AC ammeter now indicates that there is a load on the generator. Positioning the generator switch to off opens the associated generator breaker. The IDG is no longer supplying the associated transfer bus. The generator off bus light illuminates when the associated IDG is not supplying the respective transfer bus. APU generator output can be connected to either the number 1 or number 2 transfer bus by means of the two APU generator switches. A blue APU generator off bus light illuminates when the APU generator is ready for electrical load but is not connected to either transfer bus. Click on number 2 APU generator switch to continue. Placing an APU generator switch to on when both IDGs are powering their respective transfer buses will disconnect the IDG power from the selected transfer bus and replace it with APU power. The other transfer bus is still powered by its respective IDG. If the transfer buses are powered by the GPU, placing either APU generator switch to on will disconnect the GPU power from both transfer buses, which will now be powered by the APU generator. The opposite source off light will illuminate to indicate that no power source has been selected to power the related transfer bus. Placing the remaining APU generator switch to on will extinguish the source off light. The bus transfer switch controls the operation of the bus transfer system. It is a two-position switch guarded to the auto position. If a transfer bus is not powered, the associated transfer bus off light illuminates. The electric annunciator light and the master caution lights also illuminate. With the bus transfer switch in the auto position, a bus transfer relay automatically connects an unpowered transfer bus to an operating AC power source. The powered transfer bus now supplies both transfer buses. The transfer buses can be powered by any operating generator or the GPU. Click on the bus transfer switch to place it in the off position. With the bus transfer switch in the off position, the automatic bus transfer system is deactivated. Therefore, the operating AC power source will not be able to power the unpowered transfer bus. The off position of the bus transfer switch will open the cross-bus tie relay. This affects the backup capabilities of the TRs. Recall that TR1 and TR2 are able to provide alternate sources of power for each other, and that TR3 can back up TR1 or TR2. The auto position of the bus transfer switch closes the cross-bus tie relay and allows the TR to provide this backup capability. With the bus transfer switch in the off position, the two DC buses are isolated from each other. The transfer buses can also be powered by an external electrical power cart or GPU. The application of GPU power is controlled by the ground power switch. The switch has three positions: on, off, and spring-loaded to the center neutral position. It controls the ground power relays and enables the GPU to power the transfer buses if the GPU power is within limits. Illumination of the ground power available light indicates that a GPU is plugged in to the external AC receptacle. The light will only illuminate if the GPU power is within limits. Click on the ground power switch to place it in the on position. Placing the ground power switch to on will connect external power to both transfer buses and remove the previous power source. Recall that it is not possible to power one transfer bus from the GPU and the other transfer bus from the APU. Therefore, if the APU is powering both transfer buses, placing the external power switch to on will disconnect the APU power from both transfer buses, and they will now be powered by the GPU. We will now look at the battery switch. The battery switch is a two-position switch guarded to the on position. When the switch is on, the switched hot battery bus is powered and the automatic switching of the standby system to battery power is armed. Click on the battery switch to place it in the off position. When the battery switch is off, power is removed from both the battery bus and the switched hot battery bus if normal power sources are available. However, if the battery is the only power source, power is removed from the battery bus, the switched hot battery bus, the DC standby bus, the static inverter, and the AC standby bus. Now let's look at the AC and DC metering panel. DC loads and voltage are displayed on the left-hand side of the AC and DC metering panel. The DC meter selector selects the power source to be monitored. The standby power and battery bus positions only display voltage indications. The battery positions display the voltage and amperage loads of the respective batteries. When the battery charger is operating, the meter indicates 22 to 30 volts with a positive amperage. When the batteries are fully charged, the voltage will remain at 28 and the amperage indication will be near zero. Each transformer rectifier can be monitored individually by placing the meter selector in the desired TR position. The normal output of a TR is 24 to 30 volts. The amperage will vary with the demand and will read with a slight positive reading to the TR limit of 75 amps. Positions TR1 and TR2 indicate the voltage from the associated DC bus. Position TR3 indicates the voltage straight out of TR3. A zero amperage reading implies a malfunctioning TR even though its voltage appears to be normal. TRs never display a negative reading. The test position is used by maintenance. AC power information is displayed on the right-hand side of the AC and DC metering panel. AC amperage is read in the middle of the bottom of the display. The power source to be monitored is selected by the AC meter selector on the right-hand side of the panel. Engine and APU generator outputs are identical. These generators and the ground power cart normally produce 115 volts AC at a frequency of 400 Hz. Selecting standby power displays the frequency and voltage of the AC standby bus. Normal frequency and voltage are 115 volts and 400 Hz regardless of the power source to the bus. The inverter position checks the static inverter voltage output similar to the standby power position. The test position is used by maintenance. 3 annunciator lights provide additional information as to the status of the electrical system. The battery discharge light illuminates when an excessive battery discharge has been detected with the battery switch on. This light is normally illuminated when starting the APU using the battery. The TR unit light illuminates on the ground if any TR has failed. It will illuminate in flight if TR1 has failed or TR2 and TR3 have failed. The electric light illuminates if a fault has been detected in the DC or standby power system. This function will only operate when the aircraft is on the ground. Let's look at how the galleys are powered. The galley switch controls power to all galley buses. When the switch is placed in the on position, the galleys are powered from the transfer buses. The electrical system incorporates an auto load shedding feature. The system is designed so as to incrementally shed buses based on the actual sensed load. Load shed relays remove power to the galley and main buses when their loads exceed operating limits. The load shedding is handled differently on aircraft equipped with a cabin utility switch and IFE passenger switches. During a single generator operation on aircraft equipped with a galley switch, the system will first shed the galleys on transfer bus 2 when an overload is initially sensed. If the overload situation continues, the system will then shed the galleys on transfer bus 1. Finally, the system will shed main bus 1 and 2 if the overload situation persists. During a single generator operation on aircraft equipped with a cabin utility and IFE passenger switch, the system will first shed the galleys and the main bus on transfer bus 2 when an overload is initially sensed. If the overload condition still persists, the system will then shed the galleys and the main bus on transfer bus 1. If the overload condition is still not corrected, the IFE buses are shed. When the overload condition is corrected, such as bringing another generator online, the main buses, galley buses, and IFE buses are automatically restored. Galley and main bus power can also be manually restored by moving the galley switch or the cabin utility power switches to off and then back to on. If an overload condition occurs while on the ground with the APU as the sole source of power, automatic APU load shedding removes power from galley and main buses until the load is within limits. All galley and main bus power is shed when the aircraft is in flight and the APU is the only source of power. If the overload condition still exists, both IFE buses are shed on aircraft with an IFE system. Galley and main bus power can be manually restored by moving the galley power or cabin utility power switches to off and back to on after the overload condition has been rectified. In the event the APU starts to exceed EGT limits, the ECU will shed both galley buses. The main bus load shed relays will open if the overload continues. This concludes the presentation of the electrical system.